When I simplify, I try to look for perfect squares. Some of you do a prime factorization method. That's fine if it works, but it takes a long time. When you have small numbers, like 128, you should be able to use your calculator or think in your head, are there perfect squares that go into that number? 64 is the biggest perfect square, so it ends up being a one-step problem when you do that. Otherwise, you're breaking something down into all of its prime numbers and then putting it back together. When you're taking an SAT test or something that's timed, you want to save as much time as possible. What's a good perfect square to break up 75 into? 25 and 3? The mistakes we're seeing, people are continuing to put in square roots where they don't belong. Once you find the square root of 25, do you need another radical there? No. What do you do when you have whole numbers on the outside of the radical to begin with, like in number 3? It's multiplying. What do you think goes into 84? 4 definitely does. That would be 21. And I can tell 4 is the biggest because 21 can only be broken down into more prime numbers. 5 times 2 times radical 21, 10 times radical 21. Do you have calculators in front of you?
Yes.
Do 5 times radical 84. That should be close to some decimals. 45 point something. 45 points. Give me just one decimal. 8. If we have done this correctly, 10 times radical 21 should be the same decimal. Is it the same decimal?
Yes. Yeah.
That's not a perfect check, but it tells you that you're at least on the right track. You still have to verify that you have something that's simplest. It might equal that, but it's not always going to be simplest. We can't break down the 21 into anything that's helpful, so that is the simplest radical form. This year we do a little bit with radicals. Most of the time we'll take a look at rounded versions of your answers. Next year you'll deal with the radicals a little bit more. And that's why we're doing this little review, especially rationalizing denominators. Rationalizing the denominator is our fancy way of saying we're going to make the bottom of the fraction into a whole number. To start with, let's change this into 2 separate radicals. That's one of our radical rules that hopefully you saw back in algebra. This is usually one of the later topics in the year, so you might not have seen all of this. Anybody remember how you get rid of a radical off the bottom of a fraction?
Multiply it to the top.
Times what? Radical 7? Yes. The idea is that when you do that, what's square root of 7 times square root of 7?
49.
What's the square root of 49? 7. So you end up with a denominator that's a nice number to deal with. It's a nice whole number instead of a radical. Whatever happens on the top happens and you deal with it. We'll get radical 168 on the top. And if you can simplify that, you go ahead and simplify it the same way we did with the problems right above. What number do you think you can divide 168 by? Perfect squares. Give me perfect squares. If it ends in an 8, what do you think it's divisible by?
8.
Perfect squares. You got to think of perfect squares. Radical 4 times what?
42.
42. And all of that will equal 2 radical 42 over 7. Can you break down 42 into anything useful?
No.
21 times 2, those aren't perfect squares. 6 times 7, those aren't perfect squares. 4 times 42 gives me 168.
Oh, that's good.
How you got 7 again? How you got 7?
Up here, we are multiplying straight across. So I'm skipping a step. What is 7 times 7?
49.
So you have the square root of 49, but what's the square root of 49?
7.
I'm not showing that step because you never have to deal with it. Whatever's inside the radical is the answer to that multiplication. Think about what you're saying. The square root of 7 times the square root of 7 is going to equal 7. Always check to see if the whole number portion of the fraction can be reduced. Can you reduce 2 over 7? No. So we're probably okay with that answer. To check yourself, everybody put that into your calculator. Put radical. You might have to do something with the parentheses. I recommend putting fractions into parentheses. I think that the radical starts the parentheses for you, and then you just have to finish the parentheses. What decimal do you get out of that? 1.85?
I got 20. I got 20.
So approximately 1.85. Check and see if this gets you approximately 1.85. This is a simple way to kind of check. It at least tells you that it's equivalent to the original. If you're dealing with a fraction, I recommend you hit the enter key after you do the top part. Do the numerator, hit enter, then divide by 7. It saves time on errors. Sometimes the 7 might get added into the radical. Get 1.85. So it looks like we're getting the same thing. So at least it's equivalent. We're on the right track. You double check to make sure that the radical 42 can't be broken down into anything useful. The reason why we do this is just so that if we want to do something more with the fraction, you've got a nice number for the denominator. Why is that important? Well, if you add or subtract fractions, what do you have to have? A common denominator. And what's going to be easier to figure out a common denominator for, a radical or a whole number? A whole number. So that's really the reason why we're rationalizing. You'll use that more when you get to Algebra 2. The reason we're doing it is because some of the answers that we get have radicals like this. And if you're looking at a standardized test, they're not going to show the form with the radical on the bottom. They're going to show the rationalized form because it's considered simplified. So what should I do to number 5 to rationalize the denominator? Square root of 5. Why am I allowed to do that? Doesn't that change what it is?
Change what?
Doesn't that change the value by when I multiply? What am I actually multiplying by? What's anything over itself?
1.
1. When you multiply by 1, does that change anything?
No.
That's why we're allowed to do that. It doesn't change the value, it just changes how it looks. You can only multiply radicals times radicals. So I get 3 radical 40 on the top. What do I get on the bottom? 5. You never have to think about that. If you're doing this right, you're getting the whole number on the bottom. Can I break up radical 40? 4 and 10. What's the square root of 4? 2. What do I do with it? multiplied. Everything's being multiplied. So I'm ending up with 6 radical 10 over 5. Can I reduce the whole numbers at all? 6 over 5.
No.
No. So that is probably what I need. Can I break down radical 10 into anything useful? No. What am I going to multiply by in number 6? Radical 12. That gives me 4. Radical 36 over 12. What is radical 36? That's 6. So that's really 4 times 6. That's 24 over 12. That's 24 over 12, and that's equal to 2.
Okay.
On your paper, in the next section, do you have a little section that mentions Pythagorean triple?
Yes.
Pythagorean triple, fancy way of saying whole numbers that make a right triangle. You know the Pythagorean theorem. You know a squared plus b squared equals c squared. And we'll be using that a lot this year. But you don't want to use it all the time. You want to save time and energy, especially when you're taking SAT tests or standardized tests. So if you see combinations like 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, and 25, you know that they make a right triangle every single time. Have we seen 3, 4, 5 a lot?
Yes.
Yeah. So if you see a 7 popping up in a right triangle and a 25 for a whole or a hypotenuse, if you've memorized this, what should the other leg be? 24. Let's do the actual Pythagorean theorem for these three. Get in the habit of writing down the formula. Some people write it that way. I write it like this. Get in that habit, and that will help with the second side of this worksheet. What am I going to put in for C? X. I'm actually looking for the hypotenuse. 9 squared, 12 squared, 144. What's my final step when I'm using the Pythagorean theorem?
Oh, square root.
Probably the square root. X equals 15. This year we're only interested in the positive value because we're looking for a length. Next year you'll be looking at positive and negative 15 when you're dealing with quadratics. What am I looking for in number 2? I'm looking for one of the legs. What should be in for the c squared? 34. And then I've got x squared, and I've got 16. $11.56, $2.56. What's the extra step that is thrown in when you have to find a leg? A little bit of subtraction. I'll do square root. What's x? We get a leg of 30. This time we not only have a right triangle, what other type of triangle is there? If you have x and x, what kind of triangle? Let's put in some slash marks in there. It's isosceles. Let's remember our algebra skills. What is x squared plus x squared? 2x squared. You have two of them. Treat them like objects. If you're squaring something with a radical, you got to square everything. So square the 7. What is that? 49. What happens when you do a radical times a radical? You get the number.
No, 2.
So I'm skipping over the step where you get the radical 4. What's the radical 4?
Oh, okay.
2. So you square the whole number, and the radical times itself is going to give you the whatever number's inside of that radical, which is 98. What should I do first before I take care of the power of 2? I got to take care of some division. I want to isolate that variable as much as possible before I do the square root. X equals 7. When we get to section 4, we will take a look at this and find a shortcut for this type of problem. You could have actually done all 3 of these with a shortcut, because this is a 3, 4, 5 multiple. Not only do these Pythagorean triples make a right triangle, but every multiple of them is also automatically a right triangle. So when I made up these numbers, all I did was think to myself, what's 3 times 3? What's 4 times 3? What's 5 times 3? 15. If I multiply any Pythagorean triple by the same number, whatever results, and in this case we got 9, 12, and 15, I know that the result of that will be another Pythagorean triple. How about the next one? We ended up with 16, 30, and 34. What Pythagorean triple is that based on?
8, 15,
8, 15, and 17, which is one of our basic triples. So I used this triple and this triple, multiplied them by some number. What did I multiply by in the second one to get from this to this? 2. What did I multiply by to get from this to this? 3. You multiply by whatever you want. I could make a Pythagorean triple 30, 40, 50. I know right away that's a right triangle. I know that 80, 150, and 170 is a Pythagorean triple. Next page, try problems 4 and 5. You know you have to do the Pythagorean theorem, but you got to do a little more work on top of it. Try those 2. Looking at number 4, did everybody realize that when you see a altitude within an isosceles triangle, that means that it splits that in half?
Yes.
So in effect, it's a perpendicular bisector. So this is 9, this is 9. You're just focused on one triangle, where you've got the x, the 9, and the 41. 41 squared, 18 squared. That's it. No, what should be there?
That was good there. Say 18.
There we go. Is that better? And that's the mistake that people are going to make. They're going to put in the 18 instead of the 9. If I do a little subtraction, I get x squared equal to 1600. Little square root x equals 40. Always ask yourself, does it make sense? It's a leg, so it should be less than the hypotenuse. Is it less than the hypotenuse?
Yes, barely.
Did everybody do this?
Yeah, no. Yes.
One of the new tools that we're going to use as we move through the next section of proofs is the procedure to put in a segment into a drawing. Maybe by putting a segment into a drawing, you create more information. If this is x over here, what are we going to call this distance?
A Y.
X. It's got to be the same distance because it's at a right angle, because that's the way I drew it. If this is 17, then what is this distance right here?
17.
Put a 17 there. That should now help you find this distance over here, because we know from here to here is 46. You have a 5, then a 17. How much is left over for the remaining portion? 24. Now I have a right triangle over here where I know 2 of the sides and I'm looking for one of the legs.
That's the Pythagorean triple. It's a 7.
Somebody just said it's a Pythagorean triple?
Yeah, it's a 7.
You've got 24, you've got 25 as the hypotenuse. What's the remaining Pythagorean triple? 7. You can go through the process of the Pythagorean theorem, but we know 7, 24, and 25 make a right triangle. That's 7, and this is also 7 over here. Yep. Did you see how we got to 17? Since we came straight down, this distance has to be the same as this. Well, you've got 3 parts to this, and you already know the 5 and the 17, which is 22. So I did 46 minus 22. I just added up these 2 portions. And this just was a Pythagorean triple. Yep.
I don't understand the triple.
You can go through the Pythagorean theorem with the 24 and the 25, and you will always get 7. So since 7 and 24 are pretty basic numbers, pretty small numbers, and they always make a right triangle, we try to memorize some of these that come up quite often, and that's one that comes up quite often.
But why do you like the 7? Or you said 24 and 25, get 7, right?
Yep.
Like what?
Because if you do the Pythagorean theorem with 24 and 25, you'll get a 7.
Okay.
Instead, we're just doing a shortcut. Instead of always doing the Pythagorean theorem, see if you can memorize a couple of them. This is why I've been saying try to put c squared off to the left, because it makes it easier for the way I present the next rule. Not all triangles are going to end up being right triangles. Let's put right triangle right here, because that's what happens when you get c squared equal to a squared plus b squared. If you set up c squared on the left-hand side of your inequality, and it turns out that you get a less than, what do you think the answer is? Acute or obtuse? It's acute. It's pretty intuitive. The less than should make you think of acute triangle. So let's throw in some numbers. Maybe it turns out to be something like 50, 60, and 70 degrees. To get to the specific angle measurements, we're going to have to wait until we get to the end of the chapter when we're doing sine, cosine, and tangent. When you're looking for specific numbers, then we're going to get into trigonometry. What does trigonometry start with?
Try.
T-R-I. Triangle.
I was gonna say you gotta try.
So what would you guess a greater than means? Obtuse. Triangle. And once again, these rules only make sense if you're putting the c squared on the far left. If it's reversed, then it's opposite. You'd be looking at a greater than over here and a less than over on this side. So try to keep the c squared off to the left when you're dealing with this rule. And over here, maybe we'd have something like 120 degrees, 30, and 30, something like that. Just as an example. Don't forget everything you've done up until this point. If you look at the directions for this next section of 4 problems, there's a step 1, and then there's a step 2. That implies that there's 2 things that you have to do. Back in chapter 5, if I handed you 3 lengths, like 12, 5, and 9, how would you tell if it formed a triangle at all? Which 2 should I add? What is 4 plus 9? 13. And what do I test? Is it greater than 12? So we would write down, yes, it says determine if a triangle can be formed. So I need to write a no or yes answer to start with. Yes, it forms a triangle. Now I can go on to step 2, which is what we just went over. Write down c squared, open circle, empty space. Put a question mark in there if you want. We don't know what the relationship is yet between the sides. If it's less than, what is it? If it's equal. If you get a greater than, then it's an obtuse triangle. So let's put this in. What do you think you should be putting in for C, the C? The 12. Put the largest one in for your C. Make sure you square it. And I still don't know what the relationship is yet until I get to the end. 4 squared, 9 squared, 144, 16, and 81. I'm getting 144 is greater than 97. What type of triangle? So first I answer yes, it is a triangle. What kind of triangle? Obtuse. The mistakes we see, people want to start squaring right away. And they start squaring when they're doing the first test. The first test, we don't square anything. We just add and compare. We only start squaring when we want to actually classify the triangle. So think of it as 2 steps, and you won't skip that first step. Is 7, 7, 8 a triangle?
Yes.
That's greater than 8. We can write yes. Now I can move on to writing my formula. Substituting in the larger one over here. I'm getting 64 less than 98. What does that mean? Acute triangle. Some people like to put question marks in all of these spots. You are going to want to write equals down every single time because you're so used to the Pythagorean theorem. Try to remember that you don't know the relationship at the start of this problem. Resist the urge to write down equals unless you truly have something that's equal. Is 5, 17, and 23 a triangle?
No.
Add up 5 and 17, that is equal to 22. 22 is less than 23 not a triangle. If it's not a triangle, then I can't possibly classify it as a triangle, and I'm done. Don't do more work than you have to. Next one has a radical. To start off with, it would be a good idea to have an approximation in your head of what this actually looks like. So on your calculator, do 4 times radical 3. Get a decimal approximation in your head. What is it? So 6.9 something approximately. So when I test it, use the decimal for your step 1. So let's do 4 plus 6.9. That's about 10.9. Is that bigger than 8? So that at least gives me an idea that yes, it is a triangle. It also gives me an idea as to which number is largest. Maybe the one with the radical is the largest. You don't know until you actually take a look at the decimal. Which one's the actual largest in this case?
8.
8. So when I go to take a look at c squared and a squared b squared, I know to put the 8 over here. What do we want? We want 4 here, and we want to go back to the exact radical. I don't want to put in 10.9 because that's an approximation. So I need to have 4 radical 3 squared. I want to deal with something exact for as long as possible. 64, 16. What happens when you square something with whole numbers and radicals? Square the whole number and what do I get? 16. Square the radical 3 and what do I get? So I end up with a 3. 64 is 16 plus 48. 64 equals 64. So I didn't know. Now I know. What does that mean? This is a right triangle. Even though 4 radical 3, and 8 make a right triangle, why isn't it considered a Pythagorean triple?
Because it's not one of them. They're not integers.
JP, a little bit louder.
They're not integers.
They're not integers. We use the term Pythagorean triple when we have whole numbers. And here we've got 1 for the radical. So it makes a right triangle, we just don't classify it as a Pythagorean triple. What do you think? Is that a pretty easy way to start off chapter 7? You got a few things to memorize. The rest of the chapter is taking care of shortcuts and details and figuring out what these sides are and what these angles are exactly, or to a certain degree of precision.